Okay, good morning, everyone. My name is Andrea Arcuri, and I worked for quite a few years as a consultant, but a couple of months ago, I lost my sanity and I went back to academia to work as a professor. Hopefully, there is a cure for that, but we'll see. Anyway, thanks for attending this talk. What I'm going to talk about today is about how you can automatically generate test cases. That's the idea. So I want to start with this picture that I'm Italian and I live in Oslo. So I took this picture in the metro of Oslo with my mobile. And I like this picture because, as you can see, in the metro, when you go down, there are all displays of advertisement. On that particular day, all of them crashed. Now, I don't know if it was an hardware problem or a software problem. I don't know. But I like this picture because it reminds me how bugs are so common. And another important thing, it reminds me that not all bugs are bugs. Sometimes they are features. In my particular case, as a user of the metro, I don't want to be bombarded by advertisement. So in that particular case, for me, it was a feature. Anyway, the idea here is, will it be nice to be able to test software automatically by just pushing a button? Wouldn't it be great? I mean, for a lot of developers, for a lot of people, testing is a tedious task. I mean, who in this room can say, I love to write test cases? One, I saw maybe one hand. Two, okay, good for you. I like to write test cases as well, but most of the developers usually find it as a tedious task. I mean, it's something that you have to do because it's important. You have to make sure that your software is correct. But a lot of people just don't like to write test cases. It's just a burden. And when I'm talking about test cases, there is a lot of type of testing that you can do. For example, there is unit testing, integration testing, end-to-end testing, performance testing, a lot of kinds, security testing. So I cannot speak about everything. I have to make some choices here. So I will just focus on what maybe is the easiest among the testing, which is unit testing. And so, just to make clear, when I'm talking about generating unit tests, I'm speaking about object-oriented software, Java, C#, for example. How many people here are Java developers? Raise your hands. Okay, how many are .NET developers? Okay, quite a few. So I will have some example. Most of the things I will show will be in Java, but it will be very, very small example. So hopefully, even if you have a background from C# and you haven't never seen a line of Java, it might still follow up. And most of the discussion that I will do will actually apply to both. There isn't really much difference apart from the tooling. So, object-oriented software, then a set of class under test, that is what you want to generate test cases for. And then for each class, you want to generate unit tests automatically, with some goals in mind. Like, for example, you want to maximize some kind of criteria, like, for example, instruction coverage. You have your software with maybe hundreds of thousands of lines, or maybe a class with just 500 lines. And one of the goals, maybe when you write test cases, is try to cover everything in that class. That's a possibility. Another thing is that not only you want to maximize the coverage, but when you generate those test cases, you actually want to check what is the expected result. So a lot of time you write assertions to check actually what the test case is doing. Another important thing of assertion is because now you're asserting something in your test, and then you can use those test cases later for regression in your continuous integration servers. And another important thing is that you don't want millions of test cases. Even if you manage to generate them automatically, you want something small. Because you might want to look at them, and you don't really want to look at 1 million test cases. And other things are that you might want to add them in your repositories like Git and so on. You don't want to have millions of extra files there, because it also will increase compilation time. So the idea is that you want to generate test cases, should try to maximize some criteria, like code coverage, and then you want to add assertions, and you want them small. You don't want millions of test cases. So let's make an extremely complicated example that fits in 3 lines of a function that takes as input 2 integers and divide them. Very complex. And for example, if you want to divide by 0, actually you should throw an exception and say, no, you can't divide by 0. So what type of test you might want to write this? It's very simple. You might maybe have, for example, 2 test cases. One with some valid inputs, like 3 and 2, and then you check the expected result. And then you also want to consider the other special case, in which you divide by 0, and you actually want to expect that what you get out of it is actually an exception. That exception that I have in the code was actually thrown. Simple, but actually even in a simple case like this, for test generation is a problem. Because first of all, there is a bug. 3 divided by 2 is not 1.0. It's 1.5. So first of all, there is a bug. And the problem here is that how can a computer knows that it's a bug? I mean, you, as a person that knows about divisions, knows that if you divide 3 by 2, it should be 1.5. But a computer that tries to generate test case automatically will have no clue. I mean, it can still generate it, but it can only record what was the actual output, which in this case was 1.0. So it's useless? Maybe, maybe not. Because first of all, if a number of test cases that are generated are just a few, you can look at them. You can look at them and see, 3 divided by 2, I get 1.0. OK, there must be a bug somewhere. That's an option. But in that case, you have to look at the test cases. Another option is regression. But even if you're not sure if those assertions are actually correct, you can use those test cases later on in continuous integration testing and check if one day it breaks. Because if those test case breaks, maybe there was a change that actually introduced a bug. So there are different kinds of scenarios. So as I say, here, if I want to generate those 2 test cases automatically, I have 2 problems. How I choose the inputs in the first place. Like here was 3, 2, 0, and 0. How I chose those values out of the 4 billions that are available. And the second problem is how to detect if there was a bug. Sometimes I might, maybe if there was an exception that wasn't declared, wasn't expected. But I can use it as a kind of oracle and check, OK, here there was an exception that wasn't supposed to happen. But in a lot of the cases, the only things I can do is just record what was executed. So the easiest, if I have to write a system, a tool to write these test cases automatically, the easiest things I can think of that I can start from is just do things at random. So for example, if I have a class, I can start to call its methods at random. If I have some inputs, I will put random inputs. Then I will check what happens. I mean, I execute the class, the method with those random inputs, and I record the output. And once I have input-output, I just output it in a JUnit file. So if you think about a random testing tool, it could look like this. Like, for example, you take a class definition as input. N might be the number of test cases that you want to generate, 5, 10, 20. You can use reflection to check what is in that class. So you might start maybe to iterate over all the methods. Then for each input on that method, you get a random value somehow. If it's an integer, it will be a random integer. If it's a string, it's a random string. You execute it. You invoke that method with that random input. And then you get the result, and then you write it on a JUnit file. So this is how high-level a random testing tool will look like. So to make it a bit more complete, let's actually have an implementation for that specific foo function. And again, these are just simple examples. I can't show you 2 million lines of code here. I need something simple that fits in a slide. So if I just want to focus on that specific function and not have a generic tool, but just to show you I have an idea, a grasp of what can be done, this is an actual function that will generate test cases, JUnit, automatically for that method. What it does, for example, here it generates 10 test cases, takes an X at random, a Y at random, it executes it, full divide for those 2 values, get the result, and then I just output the test like it was a JUnit as a string. So if I actually run this thing, what I get is this. I actually get 10 valid JUnit test cases that compile. I can just write them on a disk, on a file, compile it, and add it as part of my test suite. It works. I mean, it's exactly this one, just 5 lines of code. It's nothing, it's not rocket science. Problem here is that the values are at random, so it's not really easy to read them. I mean, I guess that -19605800656 divided by 5 to blah, blah, blah is equal to -3. OK, fine. I guess I will just trust it. I mean, it's just that it's actually recording it. But if you just think about generate test cases, that works. For that particular case, I mean, you need 1 million test cases tomorrow. You can generate it like that, if you just care about numbers. But of course, these are kind of useless. Why are they useless? Because, for example, they never called that method with 0 as the denominator. So it actually covers only one branch. So there are some problems here. It's not as easy as it sounds. It actually is very inefficient. One problem is how many test cases to generate. 10, 20, 50, 1 million, 20 millions. Who say 30 millions? No one for 30 millions? I see maybe 40 millions there. No, OK. The point is that you can use criteria to choose how many test cases you want. For example, things you can look at code instructions. You can use tools like Jacoco to measure code coverage, and you only keep test cases that increase coverage. If they don't increase coverage, you just throw them away. It's an option. I mean, there can also be other options, but that is a simple one that might work. But the other main issue here is how I can generate test cases that can cover all of the cases in my software. Because even on that trivial example of 2 numbers divided by each other, I don't manage to generate all the test cases that can cover all the possible branches. And the problem is that the only way to get it is to get a y equal to 0. And there are 4 billion values in an integer. So on average, I will need to generate 4 billion test cases before I manage to cover that trivial software. So already for trivial software, this doesn't work. I mean, you can play with it if you want, but not really. It's just more a toy, not something that you can really use in production. So can we be smarter than random testing? Yes, there are some things that we can try. One of the easiest things that you can think of is kind of seeding. I mean, when you test a class, you will need to load it with a class loader. And while you load it, you can actually look at the bytecode. You can actually look at the constants that are there. So if a class is using constants like 0, 5, and 10, you maybe exploit that information. And it's not only about integers, it's also about strings. And then from those, all these constants that are using the software, you can try to create a pool of values. And when you sample, instead of sampling at random, you can do something like this. That, let's say with 50% probability, you sample completely at random. Otherwise, you sample from the pool of constants that were used in the software. So the extended version of this random testing tool for that specific class is just like before. It's just that I have a pool that, in that particular case, I just code it directly. I mean, in the software, there was at 0, so I just use it 0. But of course, you will have to make things more complicated to actually automatically extract those constants from the bytecode when you load the class. But I'd say this is just to have something that fits in one slide and that I can actually execute. The other tricky thing here is that now I'm actually going to get a y that is equal to 0. And when I call the method, it will actually throw an exception. So I actually have to catch it. And based on whether there is an exception or not, I will write a JUnit test differently. Because if there is an exception, I actually have to check that the exception was thrown and fail otherwise. And as again, this fits in a slide, and I can execute it. And when I execute it, I get this. I can actually now manage to cover all the possible cases. Because I actually get methods here in which that divide is called with 0. So relatively simple, and in this particular case, I actually managed to cover everything. And as I say, this code is just specific for this function, but you can write it generic. And as I say, it's not only a matter of integers. You can do exactly the same with strings. For example, if you have a function that takes as input a string value, and you have some branches in a switch based on those strings, you can use the same technique. Instead of generating completely at random, you can look at what is in the bytecode, and then sampling from this pool, in which it will work just fine here. Problem is, it's not so simple. I mean, if it was so simple, everyone would do it. It's already on trivial example, it doesn't work. So let's consider this trivial example in which I get as input a value, and I have a very complex predicate with say value times 2 equal 42. Very complex. And I want to manage to cover it. Actually, using CD makes things even worse. It actually was a bad idea. Because here, in my pool, when I look at the bytecode of this function, there is the value 2 and 42. But the solution is 21. So every time that I sample from this pool, I go nowhere. It's actually worse. At least if I sample completely at random, I have a probability 1 out of 4 billions to actually get it. But if I sample from the pool, it's completely pointless. You will never get it. So, random testing, even on trivial things, on trivial software like that, doesn't work. I mean, unless you want to generate trillion and quadrillion of test cases, it doesn't work. So the one thing is that you can define the generation of test cases like it was an optimization problem. And then you can use any kind of search technique to try to generate those test cases. But what we want to optimize here, what is our goal here? In this particular case was code coverage. But again, if you have other criteria that as long as you can define them, you can use them. Doesn't really matter. So when we're talking about search algorithm, and as I say, there are things like climbing, simulating annealing, genetic algorithms, and so on, and so on, and so on. There are 3 things that are extremely important to understand. One is the concept of search space, the concept of search operators, and the concept of fitness function. So are the 3 main things that are practically the same for all kinds of search algorithms, and also for all kinds of problems that can be modeled as a search problem. Let me give you some more details on each of them. The search space actually defines the solutions of your problem. For example, if your problem is to find the test data for a function that takes as input 2 integers, your search space is the space of all possible combination of 2 integers. But if you're talking about object-oriented software, in which a solution to your problem is a test case that calls methods, create new instances of objects, and so on, you need to consider all of them. So in that particular case, it will be a sequence of function calls of different lengths. So even on very simple problem, the search space is huge, extremely large, even on trivial problems. Even if you have one single integer, that is already 4 billion combination. Think about a test case that has 10 methods from maybe 10 different classes. Again, it's extremely huge. And when it means that it's extremely huge, you cannot enumerate all possible combinations. That just doesn't work. It will just take forever and ever. Other concept is the search operators. It's how you explore this landscape, this space of possible solution. Because as I say, you cannot look at all of it. It will just take infinite time. So somehow you will need to start from somewhere, and from that somewhere you will need to explore the area to try to find better solutions. And how you do it, most of the time you do small changes. For example, if your space is a space of integers, and you start from 500, you can look around. Maybe 501, 502, 480, around that area. You will not jump directly to 1 billion. So somehow, you need to start from somewhere and then do small modifications. Modification, when you're talking about test cases, could be remove a statement, add one test case at one instruction at random. If there are some integers in the test case, you can do plus minus 1, Same if it's a string, you can change some characters. Small changes, but usually at random, because you need to explore the search landscape. Once you do that, it's still not enough. I mean, even if you have a way to explore this huge search landscape, you still need to have a way to identify if what you look at is good or not. And that is what is usually called the fitness function. It's somehow an entity, a function that tells you your solution is good or your solution is bad. So the idea is that when you're exploring, you will see some solution test cases that are bad, you forget about them. If you see that some test cases are a bit better on this area, okay, let's go here. Then I look here and say, these are still bad, no, stinky. These are better, okay, I'm going here, and so on. So you try to explore the search landscape. But to do that, you need to know how good the test cases are. So you need a fitness function, something that tells you this test case is good or this test case is bad. So there are a lot of different types of heuristic that you can define. I'm not going to show all possible of them because there are many, many. But the simplest things, just to make an example, is about numbers. Let's say that you have this case that you want to solve x equal 42. There is a predicate, an if statement in which you have that extremely complex constraint, x equal 42. You can start with two random values, 1 and 1000. Neither of them solve the constraint, because only 42 solve the constraint x equal 42. But are 1 and 1000 equal? No. 1 is a bit closer to 42, and 1000 is far away. So heuristically, if I have to make a choice between 1 and 1000, I will go for 1. Neither of them solve the constraint, but 1 is better. And again, how do I do that? The trick here is always bytecode instrumentation. One of the nice things of Java is that when you load a class, you can do all modifications you want. So the idea is that here, when you actually load the class, you start to instrument it, for example, in the predicates and so on, to actually gather this information every time that predicates are evaluated. And as I say, this works very fine for integers, but you can apply to everything, strings and so on, object as well, as long as you can define a meaningful way of distance. So in this particular case, I just take the module of the difference between the two values, x minus 42. And I try to minimize that distance, because when that distance is at 0, then it means I've solved the constraint. And as I say, it's not only for integers. You can also have for all kinds of methods on strings. There are a lot of methods on strings that are Boolean, like, for example, starts with, and you can define all kinds of heuristics, pattern matching, and so on, to try to define a meaningful distance between two values. Because once you get that distance, then you can start to explore your search landscape. Because you can try to find which are the test cases that actually are closer to solve those constraints in the if statement that can lead you to achieve higher code coverage. So that's the idea. So the simplest search algorithm that is very simple is hill climbing, which is kind of aggressive, greedy algorithm. The idea is that it starts from a random solution, completely at random. And then it starts to do small modification. For example, an integer does plus minus 1. Then, if something is bad, discard it. If something is better, it moves to this new solution. And it keeps track of one solution at a time. So in this particular case of x times 2 equal 42, start from a random solution, completely random. 15, maybe. So from 15, does it solve the constraint? No. And I say, I can instrument the code, I can execute it, I can run a test case with value 15, it will not solve the constraint. So I don't cover that if statement, so I don't achieve full coverage. But I can calculate the distance from the constraint, the heuristics that tells me how far that value is from solving the constraint. And then from that, I can look at the neighbor. I can add 1, I can remove 1. So I look at 16 and 14. 14 is worse, 16 is better. I move to 16. And I repeat. I repeat again and again, and finally I get to x to equal 21, and I solve my problem and generate the right test case. Problem is, it works on that trivial example. On more complex example, it doesn't work. So another more popular algorithm is called genetic algorithm. And I say because hill climbing is very greedy. It has very lot of limitations. It only works if you have a straight path. As soon as there are some minor issues, then it doesn't work anymore. And GAs are inspired by natural evolution. And the interesting thing is that they are used everywhere. Drug design, industrial optimization, stock trading. I mean, when you're doing optimization, most of the time, underneath there is a genetic algorithm or one of its variants. So it has a huge applications. And the idea here is that because there is a huge application, you can also try to apply them on testing, as long as you can model testing as an optimization problem. So very briefly, I mean, could be an entire course on itself. I can, just to give you a glimpse of what a genetic algorithm is. The idea is that you keep a population of individuals, of solutions. Then you calculate fitness, and the ones that are most fit, you recombine them. Then you start to do some small mutation, like plus minus one, same kind of search operators in hill climbing, and then you check if you get something better, you keep it in your population. If something worse, you just throw it away. That's the idea, very, very high level. So let's make an extremely complex example now. If I have a constraint, now I have two constraints. X equal 2 and X times Y equal 42. Very complex. And let's say that you have a nice starting point that is 7 and 6. 7 times 6 is 42. So the one on the right side is solved. 7 times 6 is equal 42, so that constraint is solved. But X equal 2 is not solved. So I have a partial solution that solves one part of a constraint, but not the other. So if I do hill climbing and I try to do small modification, plus minus 1, I might try to get close to X equal 2. But as soon as I decrease from 7 to 6 to 6 from 5 and so on, the other constraint is broken. So I'm stuck. That's one of the examples in which hill climbing doesn't work. I can get stuck in these kind of cases. But a genetic algorithm, because it uses a population and it's not greedy, that doesn't jump directly on better solution, it can actually evade from these problems. But this might work for when you're talking about integers, when you're talking about strings, methods that take something as input. I mean, you do manipulations and you can play with these things. But the problem is that a lot of time, test cases, well, software has to work with the environment. Reading from the file system, accessing the network, user interfaces, and you might maybe decide, okay, for this type of classes, I will not generate test cases. I will not write unit test. But the option is that you can still try. I mean, you might still want maybe to write unit test even in those cases. So let me make a slightly bit more complicated example. Again, artificial, just because I want it to fit in a slide. I might have a function, check content, that takes nothing as input. So there is nothing as input in that method. But it reads from the file, from the console, from the terminal. What it reads is a name. Then you check if there is a file on the file system with that names, and it reads its content, and then it checks if the content of that file is actually equal to the current to-date date. Artificial example doesn't do anything useful, but just to give you an example of having a class that actually has to speak with a console, has to maybe read things from the file. And the interesting thing is that even if you manage to write a test case for it, it will pass today, but it will fail tomorrow, because you don't have direct control on the CPU clock. But the interesting thing is that you can actually manage to generate test cases for this type of class automatically. And the solution, again, bytecode instrumentation. The idea is that when you test these classes, you can actually check which part of the environment they are interacted with. And then you can simulate those environment inputs and then extend your search operator in the search to handle those inputs as well. And as I said, the key is always bytecode instrumentation. the nice thing is because it's all automated. When you read a class, you can do whatever you want with that class. So here is that for each class that can interact with the environment, you can actually mock it out. You can have another class with exactly the same semantics, but instead of working, for example, on the real hard drive on your laptop, it's going to work on a virtual file system. And for example, if your software you have something like file f equal new file, the bytecode instrumentation will replace that new file with a new mock file. And you can do it for all kinds of operations in Java I/O. And from the point of view of a system under test, there is no difference, because if you write those mocks on working on a virtual file system. But not just I/O, you can do the same things for the CPU clock, networking, TCP, UDP. And then, once you have that, you can add search operators in your search to generate those inputs. What are search operators here? Methods to maybe create files, methods to maybe to change the time of a CPU clock. But of course, you only add them if a system under test, if a class you want to test is actually interact with the environment. If it's not, there is no point. I mean, if a class doesn't read any file, there is no point in generating a file on the virtual file system. And the big question is, does it work? And if you have never heard about genetic algorithm, if you have never heard about test case generation, it sounds like snake oil, isn't it? If it's the first time that you hear about it, I mean, okay, that can be too good to be true. I mean, it's okay. But of course, it's impossible to work. But if you consider, for example, this particular case, you can actually push a button and generate all test cases that can actually cover the entire class. It's possible, at least for that example, it works just fine. You can actually generate a test case that can cover fully that class by generating events on the environment and the right input completely automatically by pushing a button. But again, that is a trivial example. Well, not so trivial, but it's a small example. How does it work on real system? And the nice things that to check how does it work on real system, there are these great things like GitHub or SourceForge or other repository in which you have millions of systems that you can try. So for example, you can download 30,000 classes, run a tool to generate test cases on those 30,000 classes and see what happens. And actually get 70% instruction coverage by just pushing a button. So it actually can work on a lot of different systems. And in that graph, it's the x is axis is coverage, intervals in block of 10%. Y-axis is the number of classes that achieve that coverage. So if I look at that graph, it tells me that there are a lot of classes in which they're trivial and can actually get a full 100% coverage. But then there is a 15% classes that those tools are completely hopeless, don't generate anything. They don't do anything there. And then there is a mixed results in between. But when you do the average, it's not bad. 70%, I mean, if you're just pushing a button, why not? Especially if you have some objectives, like you have to achieve 70% coverage on your new software, otherwise you don't get your bonuses this year. Do something like this, and even forget about the test case. You don't even need to look at them. If it's just a number, if your managers like numbers, do that, fine. Then, of course, we also try on some actual industrial systems. Same type of graph, same type of results. And then also on some artificial software, but that was different results. Well, still good, but very different results. Tools. I mean, you have listened to me for the last 34 minutes, so you might think, should I try these things? I mean, or just snake oil, I can actually try them. There are actually some tools. For Java, there is some commercial tools called Agitar1 and JTest. I don't like them, I cannot recommend them, but if you want, try them out. Up to you. But don't say that I recommend them. Then there are at least two tools that are research prototypes developed in academia. One is Randup and one is Evosuite. And the example that I show were from Evosuite. And the nice thing is that they are open source, you find them on GitHub. But those are research prototypes. You can play with them, but from playing with something and use it in production is a different story. And then for the .NET developers here, There are things that is PEX IntelliTest that actually comes from Microsoft Research, which is for C#, that can actually generate test cases automatically. Slightly different techniques. Dynamic symbolic execution is not using genetic algorithm. Well, it actually uses genetic algorithm for calculation on float values, but at high level it's using dynamic symbolic execution. And as I say, Randup is using a variant of random testing. Evosuite is using genetic algorithms. And yes, conclusions. It's not snake oil. It's possible to generate test cases automatically. There is a huge amount of research in academia, not just on unit testing, all kind of possible testing, system testing, security, and so on. There are some open source systems on GitHub. If you are curious on how actually they work internally, you can look at them. The source code is all available. But they are not really production ready, if I have to say. I mean, I wouldn't really recommend to use now today in production because they have few problems. And maybe the only exception is, as I say, PEX from Microsoft Research. If you're using .NET, you can use it. It's a stable tool. For Java, there is a lot of prototypes, but I mean, you can play with them if you want. And I think it's all from me. Thanks for your attention. Thanks.